Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today we'll perform a quick demonstration of an isolated electrically excited synchronous generator in the loaded condition. The intent is to demonstrate how varying the magnitude and reactive nature of an electrical load connected to a synchronous generator can influence the generator's output and how one can compensate for these disturbances. This lecture operates under the presumption the viewers watch the Loaded Synchronous Generators lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet or only dimly recall its contents, please bring yourself up to speed and return when you are so qualified. In the aforementioned lecture, we explained a lot of the theory surrounding how an electrical load's magnitude and reactive nature can affect a generator's output and how to compensate for these disturbances, but we never got around to performing a practical demonstration of these effects. Well, today we'll rectify that oversight and put this knowledge to use on some real-world equipment. If you recall, this collection of curves illustrate the voltage magnitude regulation characteristics for a synchronous generator with a range of load conditions. Viewers will note that resistive loads experience reduction in output voltage magnitude as current demand increases. Inductive loads experience a similar reduction effect, only more pronounced. Capacitive loads, in contrast, experience increased voltage magnitude as current demand increases. Additionally, we learn an operator can compensate for these undesirable changes in voltage magnitude by increasing or decreasing field current to return voltage magnitude to a desired specification. Note these scenarios do not account for variations in frequency and presume the prime mover is making use of sophisticated closed-loop speed control mechanisms. Part 1 of this demonstration will make use of a constant speed prime mover and explore voltage magnitude effects only. Now, the Big Bad Tech channel is not known for half-assing things, so in the aforementioned lecture, we kept hammering this topic well beyond the limits of good taste and explored how the real power needs of electrical loads can and do affect resultant frequency of isolated generators. Part 2 of this demonstration will make use of a prime mover lacking closed-loop speed control and explores both load-induced voltage magnitude and frequency effects. Part 1, Constant Speed Prime Mover. Our goal is to establish light industrial 60 Hz 3-phase AC characterized by 120 volts line to neutral, 208 volts line to line using a Y-configured synchronous generator with 2 pole pairs per phase. When the constant speed prime mover starts turning the machine at 1,800 RPM and field current is set to roughly 610 milliamperes, we observe 3-phase AC at 60 Hz and a magnitude of 120 volts line to neutral. This is exactly what we want. We will try to maintain during the course of this demonstration. Good luck with that. You'll note in this unloaded state the prime mover exerts a token amount of mechanical power, on the order of roughly 5 watts just to overcome friction. In this unloaded state, the load draws no current and consumes no real nor any reactive power. Let's put the system to work. Let's examine resistors first. Our first load profile is a balanced Y configuration of 1,200 ohms purely resistive impedances. When connection is established, voltage magnitude drops to 117.5 volts. Each resistive element draws roughly 100 milliamperes of current, consumes roughly 12 watts of real power for a total real power demand of roughly 36 watts. In order to meet this real electrical power demand, the generator consumes 39 watts of mechanical power. Given this prime mover is operating in constant speed mode, speed remains at 1,800 RPM and frequency remains at 60 Hz. Our concern is a small reduction in voltage for this lightly loaded resistive condition. This is to be expected, but not good given an electrical distribution system should ideally maintain stable voltage magnitude. A quick solution to this disturbance is to increase field current. At roughly 630 milliamperes DC of field current, voltage magnitude stabilizes at the desired 120 volts. The stable state won't last long because electrical demand is an ever-changing target. Case in point, consider a second low profile consisting of 200 ohm purely resistive impedances. When subject to increased current draw, output voltage magnitude drops to 110.5 volts. Each resistive element draws roughly 560 milliamperes of current, consumes roughly 61 watts of real power for a total real power demand of roughly 183 watts. In order to meet this demand, the generator consumes 193 watts of mechanical power. Given this prime mover is operating in constant speed mode, speed remains at 1,800 RPM and frequency remains at 60 Hz. Our concern is a small reduction in voltage for this increasingly loaded resistive condition. Again, a solution to this disturbance is to increase field current. At roughly 710 milliamperes of field current, voltage magnitude stabilizes at the desired 120 volts. All is well, but now consider what happens when this load is suddenly disconnected. In this doubly compensated state, voltage magnitude surges to 128.6 volts. To prevent damage, an operator needs to decrease field current. At roughly 610 milliamperes DC of field current, voltage magnitude stabilizes at the desired 120 volts. This confirms our theoretical expectations regarding voltage regulation for resistive loads. Notably, increased current draw for resistive loads results in decreased output voltage magnitude. A quick solution to this problem was to increase field current in response. Again, I need to emphasize this prime mover was operating in constant speed mode, thus we observed no load-induced frequency effects. Let's now take a look at inductive loads. We should observe the same output voltage magnitude reduction as a function of load current, albeit slightly more pronounced. We begin in the unloaded condition with roughly 610 milliamperes of field current establishing the desired 120 volts line to neutral. You note in the unloaded state the prime mover exerts a token amount of mechanical power just to overcome friction. In this unloaded state, the load draws no current and consumes no real nor reactive power. Let's see how the system responds to a range of inductive loads. We begin with a balanced Y configuration of 1200 ohm primarily inductive impedances. When connection is established, voltage magnitude drops to 116.1 volts. Each inductive element draws roughly 95 milliamperes of current, consumes roughly 11 VARs of reactive power for a total demand of roughly 33 VARs. You'll additionally note the inductors aren't pure inductors, since each inductor draws a small amount of real power, in the order of 1.7 watts, for a total real power demand of roughly 5 watts. Experiencing this small increase in real power demand, the generator consumes 7 watts of mechanical power. Given this prime mover is operating in constant speed mode, speed remains at 1800 RPM and frequency remains at 60 Hz. Our concern in part 1 is a small reduction in voltage for this lightly loaded inductive condition. This is again to be expected, but not good, given an electrical distribution system should ideally maintain stable voltage magnitude. A quick solution to this disturbance is to increase field current. At roughly 676 milliamperes of field current, voltage magnitude stabilizes at the desired 120 volts. This stable state won't last for long because electrical demand is an ever-changing target. Case in point, consider a second load profile consisting of 200 ohm primarily inductive impedances. When subject to increased inductive current draw, output voltage magnitude drops all the way down to 97.8 volts. Each inductive element draws roughly 490 milliamperes of current, consumes roughly 6.6 watts of real power, and 47 VARs of reactive power each, for a total demand of roughly 19.8 watts and 142 VARs. Experiencing this small increase in real power demand, the prime mover consumes 25 watts of mechanical power. Given this prime mover is operating in constant speed mode, speed remains at 1800 RPM and frequency remains at 60 Hz. Our concern is a small reduction in voltage for this increasingly loaded inductive condition. This is again to be expected, but not good, given an electrical distribution system should ideally maintain stable voltage magnitude. A quick solution to this disturbance is to increase field current. When we peg field current to the max, in this case 720 milliamperes, voltage magnitude does rise, but only to 101 volts, well shy of the desired 120 volts. This goes to show you that there are practical limits of voltage compensation. With such a high inductive demand, there's no way this generator can keep voltage stable, even in the most highly excited state. Now consider what happens when this load is suddenly disconnected. In this highly excited state, voltage magnitude spikes to 127 volts. To prevent damage, an operator needs to decrease field current. Roughly 610 milliamperes DC of field current, voltage magnitude stabilizes at the desired 120 volts. This confirms our theoretical expectations regarding voltage regulation for primarily inductive loads. Notably, increased current draw for inductive loads results in substantially decreased output voltage magnitude. A quick solution to this problem was to increase field current. This being said, there are practical limits of compensation. We demonstrated too high of an inductive demand might result in the generator not being able to meet the desired specification despite pegging field current to the max. Now let's take a look at capacitive loads. In contrast to resistive and inductive loads, which experience decreasing voltage output as load current increased, we should expect output voltage to increase as a function of increased capacitive load current demand. Let's see if this is the case. We begin in the unloaded condition with roughly 610 milliamperes of field current establishing the desired 120 volts line to neutral. You'll again note in the unloaded state that prime mover exerts a token amount of mechanical power just to overcome friction. In this unloaded state, the load draws no current and consumes no real nor reactive power. Let's see how the system responds to a range of capacitive loads. Let's start with a balanced Y configuration of 1200 ohm primarily capacitive impedances. When connection is established, voltage magnitude jumps to 126 volts. Each capacitive element draws roughly 106 milliamperes of current and supplies roughly negative 13 VARs of reactive power each for a total demand of roughly negative 39 VARs. Our concern is a small rise in voltage for this lightly loaded capacitive condition. This is again to be expected but not good given an electrical distribution system should ideally maintain stable voltage magnitude. A quick solution to this disturbance is to decrease field current. At roughly 550 milliamperes of field current, voltage magnitude stabilizes at the desired 120 volts. The stable state won't last for long because electrical demand is an ever-changing target. Case in point, consider a second load profile consisting of 200 ohm primarily capacitive impedances. When subject to increased capacitive current draw, output voltage magnitude skyrockets all the way up to 149 volts. This is definitely not good. Each capacitive element draws roughly 750 milliamperes of current and supplies roughly negative 113 VARs of reactive power each for a total demand of roughly negative 339 VARs. A quick solution to this large disturbance is to decrease field current. In this case, we'll need a substantial reduction. When we dial field current all the way down to 240 milliamperes, voltage magnitude stabilizes at the desired 120 volts. Now, consider what happens when this capacitive load is suddenly disconnected. In this highly underexcited state, voltage magnitude plummets to an almost unworkable 68 volts. To prevent damage to the grid, an operator needs to increase field current. At roughly 610 milliamperes of field current, voltage magnitude again stabilizes at the desired 120 volts. This confirms our theoretical expectations regarding voltage regulation for primarily capacitive loads. Notably, increased current draw for capacitive loads results in increased output voltage magnitude. A quick solution to this problem was to decrease field current. Alright, that wasn't too bad, was it? In summary, we demonstrated that increased current demand for resistive and inductive loads resulted in a reduction of output voltage. A quick solution to this problem was to increase field current. In contrast, increased current demand for capacitive loads resulted in increased output voltage. A quick solution to this problem was to decrease field current. Again, I need to remind you that part 1 of this demonstration made use of a prime mover utilizing closed-loop speed control and explored load-induced output voltage magnitude variation only and did not explore load-induced frequency variation. Viewers will note every time the generator encountered an increased demand in real power, i.e. primarily resistive components, and the very small non-ideal components of real-world inductors and capacitors. In these scenarios, the generator consumed more mechanical power from the prime mover. Given the prime mover was in constant speed mode, it responded with increased torque to keep speed constant. Which brings us to part 2. Part 2. Prime mover lacking closed-loop speed control. Let me begin part 2 with an admission of guilt. I am guilty not so much of lying to you, but rather I am guilty of withholding information from you. Understand I operate under the Kung Fu principle, in that I am always entitled to withhold one move from you, lest you at a later date come back to challenge me. Never forget this. The information I withheld from you in part 1 is this. Even though the prime mover in part 1 was using closed-loop speed control, it wasn't as sophisticated as I made it sound. Every time the electrical load demanded more real power, the prime mover experienced an increase in counter torque and briefly slowed down. Closed-loop speed control system recognized this fact and increased mechanical power until speed stabilized at the desired 1800 RPM. Similarly, every time the electrical load demanded less real power, the prime mover experienced a decrease in counter torque and briefly sped up. Closed-loop speed control system again recognized this fact and decreased mechanical power until speed stabilized at the desired 1800 RPM. Audibly, one can hear the generator bog down, accelerate, and eventually stabilize, as well as overspeed, decelerate, and eventually stabilize as it responded to the changing real power needs of the electrical load. The point is, even the most sophisticated closed-loop speed control system requires time to respond to changing conditions. Really, part 2 is just part 1 in slow motion. We're catching the generator's initial reaction to a change in real power demand before the closed-loop speed control system responds to this disturbance. As we might expect, any increase in real power demand means the generator needs to consume that much more mechanical power, and as a result, the prime mover will slow down. Decreased rotational speed should yield 2 noticeable effects. First, since the rotor electromagnet isn't moving past the stator poles as quickly, frequency will decrease. Second, because induction depends upon the rate of change of magnetism, voltage magnitude will also decrease. Now keep in mind this induction-related voltage decrease is on top of the load-induced voltage decrease we discussed in part 1. This means every time the generator experiences an increase in real power demand, not only will frequency and voltage decrease because the prime mover slows down, voltage will decrease again because of load-induced effects. Let's see if this is the case. We again begin in the unloaded condition with roughly 610 milliamperes of field current establishing the desired 120 volts line to neutral, the prime mover rotating at 1800 RPM establishing the desired 60 Hz. Since this is pretty critical to our later discussion, you will note the period of each waveform at 60 Hz is roughly 16.7 milliseconds. Let's see how the system responds to an increase in real power demand when I disable the closed-loop speed control option. Our example load condition is a Y configuration of 600 ohm resistors. As soon as connection is established to this load, the prime mover immediately slows down to 1768 RPM. It's kind of hard to tell from this oscope trace unless you look real close, but the period for each waveform is stretched out to roughly 17 milliseconds, which corresponds to a slower frequency of 58.9 Hz. Given a 60 Hz standard, this is roughly 1.8% off the mark. Now, this might not seem a big deal to you, but trust me, it is. A lot of devices use line frequency to perform critical timing and counting applications. And if frequency is off by 1.8%, everything you count or time is going to be off by 1.8%, and that is going to mess everybody up. In addition to a drop in frequency, you'll note that voltage appears to have dropped from our ideal 120 volts down to 115 volts. Faced with this less than ideal scenario, an operator has a couple options to bring the generator's output back inside the desired range. Principally increase the mechanical power of the prime mover to speed it up and adjust field current. My question to you is this: which one first? Speed or field current? If you said speed, you are right. Given the rotational speed of the prime mover influences both frequency and voltage, it makes sense to resolve frequency issues first, then fine-tune voltage using field current later. This way you're not undoing previous corrections. When I up the generator's mechanical power input, speed returns to the desired 1800 RPM and frequency stabilizes at the desired 60 Hz. Given this increase in speed, voltage also increases, but stops at 117 volts, just shy of our 120 volt goal. You might initially feel stuck because any further increase in speed would increase voltage, but it would also elevate frequency beyond the desired 60 Hz. Luckily, we've got one more property we can adjust to independently increase voltage, notably field current. At an increased 656 milliamperes of field current, voltage stabilizes at the desired 120 volts. Exactly what we want, 120 volts at 60 Hz. Now, before you get the false impression that compensating for each and every load scenario is as easy as I just demonstrated, let me assure you it is not. Sometimes this is quite frustrating, especially at the upper limits of a generator's rating. On a very basic level, you recall a generator converts mechanical power into electrical power. Any attempt by an operator to increase voltage, either by increasing rotational speed or field current, also mean the load will draw slightly more current and consume more electrical power. Thus, the generator again needs to consume slightly more mechanical power. Thus, it slows down just a bit, and voltage and frequency drop, which again necessitates adjustment of the rotational speed and field current, which increases voltage, which again means the load draws slightly more current and consumes more real power, and on and on and on in this vicious recursive cycle. The fact that I hit both speed and voltage with just 2 adjustments is either a testament to my inhuman skill or luck of the dumbest variety. The world may never know. The point is sometimes that there's some overshoot and undershoot of these properties and some settling time, even for the most sophisticated of systems. Ideally, successive adjustments should be smaller and smaller in magnitude than the last, and eventually the system will stabilize. This being said, it won't be stable for long, because electrical demand is again an ever-moving target. Case in point, consider what happens when this resistive load is suddenly disconnected from the generator. In its presently compensated state, rotational speed spikes to 1837 RPM, corresponding to 61.2 Hz, and voltage jumps up to 128.6 volts. Somebody better pump the brakes on this thing before it wrecks itself. When I decrease mechanical power input, rotational speed drops to 1800 RPM, returning frequency to the desired 60 Hz. At the present level of field current excitation, voltage is still a little high at 125.2 volts. When I dial field current back to 610 milliamperes, output voltage settles back to the desired 120 volts. There you have it. Part 1 and 2. Load-induced voltage and frequency variations for isolated synchronous generators. Now, before we bring this lecture to a close, keep in mind this experiment made use of an isolated synchronous generator, i.e. one not synchronized to a larger grid. An analogy might be the one generator on some island or other remote location with no other power generation facilities. Understandably, there is a one-to-one exchange between the one generator and everything powered by that one generator. This might describe one or two situations, but more commonly, as the grid experiences increased demand, additional generators are brought onto the grid through a process known as synchronization, something we'll examine in greater detail in later lectures. As we'll learn in this upcoming lecture, once a generator is synchronized to the grid, the pooled inertia of all those generators operating in time with one another largely keeps frequency constant. This is, by the way, a simplification of what we'll soon learn is a rather complex topic. Until then, this concludes this lecture. In conclusion, we performed a practical demonstration of synchronous generators in the loaded condition. We experimentally verified load-induced voltage and frequency variations and learned those steps necessary to compensate for these load-induced changes. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource and be sure to check out the Big Bad Tech channel for additional resources and updates.